Okay, for part two of this lesson on the origin of civilizations, we're going to consider the ideas of Nikolai Rashevsky on opinion formation. So the issue is that, as we've seen, in a social group or an ethnos or a civilization, people can have certain shared ideas and beliefs and values and habits and worldview. And the question is, how do people come to coordinate on those? How do they come to agree that that's the right way to behave and to think? So in one society, if people go to a wedding, they might put on a tie. And in another society, if they go to a wedding, they might put a bone through their nose. How does each society agree that that is the right way to behave when these things can seem quite arbitrary? Why in one society can everyone agree that you should wear a tie, and in another society everyone agrees that you should put a bone through your nose? And that's a trivial example, but it might be something like religion. Why does one society adopt this religion and another society adopt that religion when it can seem an arbitrary choice? How does this come about? That's what Rashevsky is concerned with, and his answer is basically imitation. If people copy what other people are doing, then they will tend to settle on one thing or another. And so let's have a look at his argument. So Rashevsky asks us to imagine a society where there are two behaviours that people can adopt, and their tendency to adopt one or the other depends upon what he calls an excitation potential. And so these curves show the fraction adopting each behaviour. So it can be up to a maximum of 1. And if we call the behaviours, that's R plus and this R minus. And I should say that Rashevsky was a mathematical biologist. So these ideas are simply taken wholesale from the ideas of mathematical biology about the responses of neurons in the brain to a stimulus that cause neurons to switch on or switch off, and that therefore cause us or organisms to, do certain things or think certain things. So that's why we're talking about excitation potential, and behaviours R plus, that's the response, R for response. And this is the plus response because the excitation potential can vary from negative to positive through 0. So when the excitation potential is positive, it adopts the positive response, or people adopt the positive behaviour. And when the excitation potential is negative, people tend to adopt the negative behaviour. But they don't just switch directly. When the excitation potential is 0, so it's neutral, there's a 50-50 split. Some will do one, some will do the other. But as the more negative the excitation potential, the more people start to switch to the negative response, and the more the excitation potential increases positively, the more people switch to the positive response. And then what Rashevsky says is, rather than considering the two responses together, we can simplify this a bit by considering just the proportion, the relative proportion adopting one behaviour. So we could take the positive behaviour. So he defines that as G, which is the difference here between the fraction doing the positive and the fraction doing the negative. So that's G. And so it's going to be, if F is the fraction adopting the positive behaviour, it's F minus, and this will be 1 minus F, because if there's F doing that, the rest 1 minus F are doing the other one. So that's F minus 1 minus F, which is equal to 2F minus 1. So we can draw how G now varies with the excitation potential. Well, when the excitation potential is 0, there's a 50-50 split between the two behaviours. So G is 0. F is equal to a half if we want to use this equation. So it's 2 times a half, which is 1, minus 1, so it's 0. So G goes through the origin there. And then when everybody is adopting the positive behaviour, so when F equals 1, the high excitation potential, then this will be 2 times 1 minus 1, which is 2 minus 1, which is 1. So G will be 1 when the excitation potential is very positive, and conversely, when the excitation potential is negative, very negative, F will be 0, and everybody will be adopting that. So that will be 1 minus F will be 1. So this will be, F is 0, so it's 2 times F, 0, minus 1. So G will be minus 1. So G varies between 1 and minus 1, and otherwise just looks like that. One and minus 1. So rather than working with this graph, we can work with this graph of G. So let's redraw this to give us some space, and we'll carry on. Okay, so here's our graph of G against phi. So we said that when everybody's adopting the positive behaviour, G tends towards 1, and when everybody's adopting the other behaviour, it goes to minus 1. And when there's it's not affected one way or the other, G is 0. There's a 50-50 balance. And again, adopting ideas from mathematical biology, Rashevsky says that when there's an external stimulus that sets the excitation potential to some particular value, because we don't know whereabouts on here we are, so we don't know what G is, but some external stimulus sets an excitation potential that will then cause G to adopt the corresponding value from this chart. The external stimulus doesn't change the excitation potential directly. It sets a target excitation potential, and then the excitation potential gradually moves towards it. So it obeys an equation like this. The rate of change of the excitation potential divided by dt is equal to phi tau or phi tau, the target excitation potential, which is determined by this external stimulus, minus the current excitation potential phi. We use tau for the target because we're already using t for time, so not to have confusion. So you can see from this then, if the excitation potential is below the target, this will be positive. Phi will increase up to that target exponential potential. And if phi is greater than the target, then this will be negative and it will move back down to the target. So a stimulus doesn't cause the excitation potential to snap immediately to a particular value, but it sets a target and the excitation potential moves towards that target. And for equilibrium, this would be equal to 0. Then the excitation potential won't change once it's reached the target. And then the question is, what sets the target potential? Well, as we said, the Rashevsky's idea is based on imitation. So the target potential, excitation potential, is set by what other people are doing. In other words, it's set by G, the fraction doing one behaviour rather than the other, or the excess fraction doing the behaviour that we're interested in. So we can write that the target excitation potential is proportional to G, what people are doing, whether they're on the positive or negative side of doing this behaviour. And so it's proportional to it, so we can put it, depends on a constant A times G. So if we put that into this equation, we get that. And we've said that for equilibrium, where the excitation potential is not going to change, this has got to equal, this will be equal to 0. So we can write, if that equals 0, then we've got, just rearranging, g equals 1 over a times phi. So this is a relationship between g and phi, and it's a straight line. We've got g against phi here. It's a straight line of slope 1 over a, and it goes through the origin because there's no constant. So we can draw that on this graph. So this is the line g equals 1 over a times phi. And we said that at these values, wherever g equals 1 over a times phi, then it will be in equilibrium. It won't move, it won't change. Phi won't have a tendency to change. So wherever this red line of g equals 1 over a phi intersects the line that tells us how g depends on phi, at those points we'll have g equals 1 over a phi, and those will be equilibrium points. So we can see we've got 3 equilibrium points here. There's one up there, the lines cross, one there at the origin, and one down here. And we've already seen this kind of thing when we talked about critical transitions. We had a graph that looked like this. This was x dot, and this was x. And we said this gave 3 equilibrium points. When down here at this, and this one is a stable point, and that's a stable point, and this is an unstable point. So we said down here, when x is below this point, x dot is positive, so it moves towards it. And when x is above that point, x dot is negative, so it moves back towards it. So that makes that stable, and similar argument here. Whereas there, where the graph goes through the origin from negative to positive, it's the other way around. That when x is below the stable point, x dot is negative, so it's moving away from it. And if x is above that point, then x dot is positive, so it's moving away from it in the other direction. So this is unstable, and these two are stable. Well, this is exactly the same as we've got here. It's just rotated a bit, but there's the line, there's the sinuous curve. It goes below and then it comes above. So we've got a similar situation. This is an unstable equilibrium, and these are 2 stable equilibria. So there are 2 possibilities then for this society. It can either be at this point or at this point. Yes, it could be at that unstable equilibrium, but it won't last long. Any slight, gust of wind will cause it to switch to one or the other. So we can see how through this process of imitation, societies can settle stably on one behaviour or the other. Wearing a tie, wearing a bone through the nose, or not wearing a tie. Okay, and now we'll just take another quick look at this again. So we've got a graph of how g depends on phi, and the line where phi is unchanging, given by g equals 1 over a times phi. And we said this came from the situation where the target excitation potential is given by a times g. And now let's consider what happens depending on the value of this constant a. So if a is large, it means that a given change in g produced, or if g is in the positive direction, if this is large, it makes a very large positive excitation potential. So people are very inclined to imitate what other people are doing if a is large. Just a small number of people adopting that behaviour causes a large tendency for other people to adopt it when a is large. Well, when a is large, then the slope is 1 over a, so the slope is small, so the slope is shallow. So if A is larger than we've drawn here, then it will be a shallower slope, which will look something more like that. The slope's got shallower. And what we can see from that is that the equilibrium points here have moved further away. So this means that the switching to the two can adopt these two behaviours, and if it adopts that one, a higher proportion of the society will be doing that. There'll be very few holdouts who are still doing the other behaviour, and if it switches to the other one, vice versa. Whereas if A is small, then it means that other people doing things doesn't really change the excitation potential very much. So people, are less inclined to imitate what other people are doing. So if A is small, people are less inclined to imitate. If A is small, then 1 over A is large. So the slope will be steep. And if A is large enough, the slope could be steep enough that it goes like that. And in this case, it misses the curve entirely, and there's just one equilibrium point at the origin. And this is now a stable equilibrium. So this means people aren't really inclined to imitate others. They basically ignore what other people are doing. They just do their own thing. And so there will be a kind of a 50-50 split just based on people's natural inclinations. Some will do that, some will do the other. So the strength of the imitation response determines the extent to which the society adopts one behaviour or another. And now let's consider what happens if there is a bias in people's tendency to adopt one behaviour or the other. So, we've so far been assuming that there's a 50-50 split in the population. Some people favour one, some people favour the other. But what if there is something external causing people to be biased, to prefer one rather than the other? So let's draw that. Here we've got our starting situation. Let's try and draw what will happen if there is some kind of bias. So let's draw another version of the chart. Well, if there's a bias, that will mean that when the excitation let's say there's a bias towards the negative behaviour. That will mean that if there's a zero excitation potential, so no pressure one way or the other, but if people are biased, there will still be a number of people who, there will still be a tendency, the majority, to adopt the negative behaviour because people are biased towards that. So even though there's no pressure, most people will be adopting, or an excess of people will be adopting the other behaviour. And the excitation potential has to increase positively quite a lot before you even get to the balance stage, where there's enough excitation to cause people to adopt the other behaviour despite their bias towards the other one. So what we'll actually get then is a curve that looks like this. Now, the whole curve has shifted along because of this bias, so that it tends more to be below the axis, even for quite high values of or positive values of the excitation potential. But our line here will still be in the same place, and perhaps I've just shifted that a little bit too much. Let's draw it a bit more like that. Then with our line we'll get something like that. So we've still got these equilibrium points there, there, and there. This is the unstable, those are the two stable equilibriums. Well, what we've seen, we've still got a stable equilibrium up here and a stable equilibrium down here. But firstly, and it is not really very clear from the way I've drawn this, I'm afraid, but this one has become even stronger. That if people are on this equilibrium, almost all will be doing that to a greater extent than over here. Whereas here, this equilibrium point has moved back and down a bit. So if they're on this one, yes, there will be the majority will be doing it, but it will be a smaller majority than before there was a bias. And furthermore, we see that the unstable equilibrium has moved closer to the stable equilibrium, so that there's more possibility if just enough people stop doing that temporarily, then it would come outside to the other side of the unstable equilibrium, and it will switch to this one. Well, again, we've seen all this before when we talked about critical transitions. We had this case where we've got these equilibrium points, and we talked about the idea, which is what we've got there, of this moving down, the graph being shifted down. So these two come closer together, that becomes more negative. The basin of attraction of this stable equilibrium point has shrunk, and there's more chance of it coming over to this one. Well, that's exactly what we've got there, just rotated a bit. And so we should, remembering what we did here, know what happens next. If we can just squeeze that on. If the bias is strong enough, shifts the graph far enough, then these 2 points up here disappear, and we're only left with one equilibrium point down there. So that if the bias is strong enough, no matter how strong the excitation potential, people will not switch to a stable situation with a majority performing the other behaviour. The bias is just too much against it. They will always come back to here. And that was the same as what we talked about in critical transitions, when the graph has shifted down enough so that those points disappear, and we're just left with one stable equilibrium point. And so the point about this is the same as we've seen in our discussion on critical transitions, that if there's a bias, then it can at first cause a gradual change in the behaviour response of the system, but then you reach a point when it must switch suddenly to the other behaviour. So it might be something like attitudes to gay marriage, or it might be a religious conversion. That this bias is people campaigning for the other view, people creating then a bias towards it, and more people are sort of have a bias, a tendency to towards the other behaviour. And at first it can see you, but if you're up here, at first it can seem though that change of attitude, well, it's just made a small difference. A few people are drifting to the other side. But if the forces that are creating the bias go beyond a certain point, then there's a sudden change. So you can be fooled into thinking, it's just slightly changing. There's just a slightly increased belief in this gay marriage or in this other religion. But then it gets to a tipping point, and suddenly your whole society changes, and you're suddenly over here, and it's caught you out. And we also saw that there's the phenomenon of hysteresis. So once you've gone past that critical point and you're down here, now you can't easily get back, because as you go to here, your stable equilibrium up there has reappeared, but the trouble is that you're in this stable equilibrium here. So there's no reason, there's nothing going to cause you to move towards that one. You'll stay at this stable equilibrium. And even when you go back all the way to here, and in fact you need to shift the bias all the way back in the opposite direction to eliminate this stable point and force the switch to the other. So basically, you've had it. Once you've gone past that critical transition and the behaviour of your society has switched, that's it. You're now going to stay there. You can't undo that. Not without massive effort.